although I have, well, it says death of stars here. It's reasonably accurate. I wrote for the name of this black holes, and I don't think we're going to get to black holes, but we'll see. We're going to, well, today, we'll get to black holes, but not today. So, death of stars. Start in death stages, or what results, what do you have left when a star dies? Let's just go with that English. What do you have left when a star dies? If you have a star that is a mass similar to the sun, you'll end up with a white dwarf. And remember, we talked about brown dwarfs, stars that are less than, what was it? About, if I remember right, it was less than 0.25 solar masses. They have complete convective mixing. And so when they run out of hydrogen, they're just out of fuel, and they just shrink and fade away. And then we had suns or stars similar to the sun. When they die, if they have masses that are between, actually, no, I think it was smaller than that, like 0.08, not 0.5. If they have masses that are between about 0.6 and 1.4 solar masses, that's a typical range. You can have white dwarfs that are less than that. But white dwarfs are when you have converted the nucleus into, or not converted the nucleus, it's held up. I'm getting everything confused in my head. The nucleus is held up by electron degeneracy. And so the nucleus, if you will, is not the nucleus of an atom. It is a bunch of atoms. Carbon and oxygen is what our sun will become. Ones that were 8 to 10 solar masses could be fair amounts of silicon and magnesium. Ones that are a little more mass than our sun will have more, what would be, oxygen. But they're going to be in somewhere in mass less than 1.4 solar masses. What do we call that number, 1.4 solar masses? Yeah, the Chandrasekhar limit. Because Chandrasekhar, is it? Chandra, yeah. He's the one who calculated that at that mass, the core will collapse. You'll force electrons into the nucleus. I'll figure it out. Well, I know that's Mira's.
Just like a raining page.
Thanks. Yeah. This is papers. I'll just hand them out. You can just sort them by person. All of this stuff should be graded. Hopefully, it's all recorded on Moodle. Hopefully, everything gets scanned, so I'm having confidence in returning them. Okay, so continuing on with white dwarfs. The Chandrasekhar limit is where you have the electrons are forced into the nucleus of an atom, which results in a massive explosion that basically converts everything into neutrons, making a neutron star if it happens in the death of a star. If it happens with an actual white dwarf later, it actually just blows up completely. So neutron stars, if it has more than 1.4 solar masses at time of death, which means more than 10 solar masses while living, then it will force the electrons into the nuclei and convert into neutrons. And the neutrons are then packed like the nucleus of a star, of an atom. So a white dwarf, they're packed as tight as you can put the electrons, but they're still individual atoms. The neutron star, they're packed like the nucleus of an atom. You may have some protons and some electrons, but it's over 90% neutrons, all packed like the nucleus. So if the density is the same as the density of the nucleus of an atom. So we take the sun will become a white dwarf that's, from what I've read, about the size of the Earth. And if the sun were to become a neutron star, well, neutron stars are only about 10 kilometers in radius. So that's much, much smaller, much higher density. And so you can see there at the bottom the density values. There are more than 3 types of supernovae. Here we have type 1a, The one we've talked about, type 1A and type 2 are the ones we talk about the most here in astronomy class. Type 1A is when you have a white dwarf that exceeds the Chandrasekhar limit and then goes kablooey. And that leaves nothing but a cloud. The type 1As are very reproducible because they always occur when you have a mass of 1.4 solar masses. They're very often going to be pretty much exclusively carbon, pretty much, over 9%. Sometimes you will have a smaller mass or a smaller one that's made out of helium, didn't have enough mass to fuse helium into carbon. Or you could have one that has significant amounts of silicon and magnesium because it had more mass. But those are very reproducible, the type 1As, because they're the same mass, generally speaking, about the same type of material. The type 2s are supernovae that occur from the core collapse of a 10 to 30 solar mass star. 10 to 30 molar solar mass star at the time of death will have a mass that's bigger than 1.4 solar masses, but less than, let's just go with that number for now. And that makes a big explosion. And then two lesser column types, type 1B and C. They result from core collapse, but they don't have hydrogen lines. Type 1C is mentioned in our textbook in this chapter as a supermassive star that has no hydrogen in the exterior, which seems really bizarre, right? You have to have a special situation to make that occur. And so they're different because something, and we're not going to go into how that occurs. So this here is a supernova remnant. You see just a big cloud of dust everywhere. Why is it lit up in bright pink? What makes stuff pink in astronomy? We had three kinds of nebulae. One of them was pink. What are the three types of nebulae? The names for them. Reflection, what do you say? Reflection, emission, and the last one is the one that sounds too dumb to be real. Dark.
Oh.
Right, you have reflection, emission, and dark. The reflection are blue like the sky for the same reason, because of the scattering of light. The emission are red. Why? Not because they're hot, because of the hydrogen Balmer emission lines.
Just kidding.
So this here is, you're probably looking at hydrogen emission lines here as well. What's the source of energy? It's going to be whatever was left from that star exploding. So here's how stellar collapse occurs according to one picture. A type 2 supernova, you have a star that's in, what stage would this be here? Red giant. And then the outer layers fall into the core. Remember, the core, you've crushed the electrons into the core, making it into basically a huge nucleus of neutrons. After it comes in and hits this huge nucleus that really could care less. The nucleus just sits there. The stuff bounces off of it like it's hard, because it's really, really hard. And energy then comes out because of the rebound effect. And that's what gives you the huge explosion, leaving behind the neutron star. Now let's talk about something that you understand, but that gets more exciting. We have stars that make a magnetic field. Why do stars have a magnetic field? Because of what? Okay, they have convection and
Can you answer the question?
why do stars have a magnetic field?
Is it the little granular things, or is that something else?
Well, we said you had to have convection to make a magnetic field, but you had to have two more things. It has to be a conducting medium that's going through the convection, and finally and most importantly, has to be spinning. Well, you have a star that's spinning, and then all of the mass falls in. And it just doesn't just fall in a little. It falls in a lot. What's going to happen to the rate of rotation if all of that mass falls in a lot? It's going to spin super fast. As it spins super fast, you're still going to make a magnetic field, but that magnetic field is going to go up as the rate of rotation goes up. So the magnetic field is going to become really strong. So that neutron star, what's left, is spinning really fast, making a super strong magnetic field. Oh, this didn't turn out as planned. Looked good on paper. I copied from one presentation into another presentation, and clearly something went wrong in the copy paste. Gamma ray bursts are an interesting thing. They're the very last thing of chapter 23. Gamma ray bursts were a mystery that is still not perfectly solved. To the best of our understanding, there are two types of gamma ray bursts that can occur. One is from the collapse of the supernova, the type 1c supernova. You get a burst of gamma ray. What is a gamma ray? Just to make sure we're clear on this. What is a gamma ray? Okay, like X-rays, but shorter wavelength, higher energy. So they're super high energy like X-rays. And so when you get a burst of this, scientists were really confused. And the two answers that our textbook gives, neither one is this one called the hypernova. It has one answer is that the type 1c supernova, without having hydrogen out there, will give you a short burst of gamma rays. Actually, no, that was the longer burst of gamma rays. The short burst is now believed to be the collision between two massive bodies, something like a neutron star and a neutron star hitting each other, or a black hole gobbling up a neutron star. Those are the things that are believed to be what causes these bursts of gamma rays. Okay, I didn't mean to have that one right in the middle. A hypernova is the same thing as a supernova, which is why it's not in our textbook, except it's when you have a supermassive star, so much mass that at death, it doesn't stop at a neutron star. You have enough mass that you can crush the neutrons. Remember, neutron degeneracy is what holds up a neutron star. If you have a star that is so massive at death that not even the neutron degeneracy can hold it apart, then it collapses into a black hole. And that's what the textbook I used before said was a prominent possibility for what causes the gamma ray bursts. So between the two textbooks, we have three different answers. One was the type 1c supernova. Actually, I say one was the type 1c supernova. It could be, if I read more carefully, this is the type 1c supernova, and I just misunderstood. The supernova, supermassive star, or the collision between two objects. Okay, discovery here. Once again, you can tell I copied and pasted. Jocelyn Bell, in 1967, she was a graduate student. You may recall I spoke about her early in the semester. She just recently was awarded a very major prize for her work. She was a graduate student back then. She gets lots of recognition, but she didn't get a Nobel or anything. What did Jocelyn Bell do? She discovered pulsars. Now, we've been talking about neutron stars. We haven't talked about neutron stars, black holes. We haven't talked about pulsars. What she discovered is something like this thing on the left, where she saw a repeatable pattern of energy in the radio range. So she goes to her advisor, because when you're in graduate school, that's what you do. And she says, look what we found. And they called them LGMs. LGM being short for little green men. Because they said, this could be a sign of intelligent life communicating with us. Now, were they serious about little green men? No. No, they were not. At least that's the best of my reading. But it was a funny thing, it could be. What if? And so in studying these, one thing she noted was that they were very reproducible. There's a very strong periodicity. It's not like it's beep, 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 beep. It's tick, 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 tick. If you look at the one on the right, you have a little variation, but the one thing that's important is you have bigger one, smaller one, bigger one, smaller one. And so these things are called pulsars because they pulse. Brighter, dimmer, brighter, dimmer. So what would cause these? As they went out searching for more of these, they found lots of these things. Some of them that have pulses that are on the order of milliseconds between the pulses, like 0.003 of a second between the pulses. And so then astronomers are, what could be making these? So there's lots of things you could come up with. One would be a star that's getting hotter and cooler. But it's physically not possible for a star to get hotter and cooler in, 0.005 of a second. It takes light more than 0.005 of a second to go from one side of the star to the other. Hence, you couldn't have light pulsing that quick. So it couldn't be light pulsing. And so other options, somebody said, well, maybe it's a star spinning. Well, if a star was spinning and making, let's say 100 rotations a second, any star would fly apart. Because inertia makes things want to go in a straight line, and the gravitational force wouldn't be strong enough to keep it going in a circle. It would fly apart. Even a white dwarf would fly apart if it was spinning that fast. The only theoretical object, and at this point it was a purely theoretical object, that could possibly spin that fast would be a neutron star. And so the conclusion they came to is these must be spinning neutron stars because that's the only thing that could spin that fast so that we have these bursts. And that is then our understanding of a neutron star and a pulsar. A pulsar is a neutron star that is emitting radiation, and if you're in the path where the radiation covers, then you see a pulse and you call it a pulsar. If you don't see the pulse passing you, then it's just a neutron star. So pulsars are neutron stars that are spinning and giving off pulses. The Crab Nebula is very important for our understanding of pulsars. The Crab Nebula was observed in 1054 AD. And given that we know when it occurred, down to within a day or two, we can look at it and we know exactly how old the neutron star is. Now in this picture, can anyone tell me, okay, this is the Crab Nebula. Remember before I was looking for it, didn't have it. Here's the Crab Nebula. You have all of this stuff here. This is a visible light picture. This is light coming from, the light coming from this Crab Nebula is about 100,000 times the amount of light coming from the sun. Enormous amounts of energy. This is almost 1,000 years old, and the remnant of a blowed up star is still giving off 100,000 times more light than our sun is. A lot of energy there, right? So where is the remnant? Here's a picture of the remnant. Right here you have a neutron star, a pulsar. Does anybody have any idea where it is in this picture?
So right there in the bottom with that little, just kidding, never mind, that's a star.
I'm going to choose yellow. I think that'll show up. I had to look at other pictures, and I saw one that superimposed different wavelengths. And with the superimposing of different wavelengths, you can see very clearly that's where it is. So that's where the pulsar is. That's where the remnant, the neutron star that is left from this explosion resides. And if you look there at the neutron star, you can see it looks like it's kind of got some steam coming out or something, and it's got a disk. That disk, of course, would be for rotation. And what looks like steam, that would be where it's giving off its radiation that's coming out because of rotation. Now, this is looking at the light from the Crab Nebula. And so if you look, these frames are each, they're matching up time for time. So this here is, I gotta change the color. Yellow does not work with this slide. Back to a nice color that works. So we have, if you look where the arrows are, you can see there's something that appears in these two right inside there that does not appear there. If you look really carefully, you might say, I think I can see something, but there's really nothing. Do you see that? That's the pulsar. It's pulsing. You don't see it in any of these. And then you see it for those two, and then you don't see it again. You have two dissimilar peaks. But as it comes around, they repeat again. The big one, the small one, the big one, the small one. So what would that suggest to you if you have the big one, the small one, the big one, the small one? Instead of them all being the same, you have essentially two types. What would that tell you? What it tells me is that there must be essentially two lights. You hit this light, it's the bright light. You hit that light, it's the dim light. So what we believe a pulsar is it's a lot like a lighthouse that's sending out two beams on opposite sides. As it comes around, you get hit by one beam and then the other. I saw an astronomy teacher doing an awesome demo. He took a bunch of tinfoil, watered it up into a ball, and put it on a drill. Then he put a flashlight in it, and he spun the tinfoil. He said, that's a pulsar. You have the flashlight, of course, you need one flashlight on each side, spinning around, and if that beam of light hits you, you see the pulse. That's essentially what a pulsar is. Now, this picture here shows something really bizarre and yet very real in pulsars. You have the magnetic fields, and how does the rotational axis compare to the magnetic field axis? It's spinning about a vertical axis. In what direction is the magnetic pole pointing? It's horizontally. So in this case, the rotation axis is nowhere close to aligning with the magnetic field axis. That's an important aspect of how a pulsar works. You have the very strong magnetic fields coming out of the poles, and as it rotates, if it's not rotating on the axis of the magnetic fields, and we know that can happen, we see that in Uranus and Neptune. It's an odd thing, but it can happen. In these pulsars, they essentially have frozen the magnetic field. The magnetic field is frozen in there, and it's rotating on a different axis. And as the magnetic field goes through space, it creates enormous forces on particles and causes them to accelerate rapidly. And as they accelerate rapidly, they give off this radiation that makes the pulses, this gamma ray radiation, because enormous energy is involved. And so these beams are caused by the magnetic field sweeping by. They are not the magnetic field. They're caused by the magnetic field sweeping by. So you have these very strong beams of particles. In 2004, the Earth went through the pulse of a pulsar. Fortunately, it was very, very, very far away from us. But it still had effects that were measurable on the Earth's atmosphere. If it had been a pulsar that was somewhere in our vicinity, the energy from those pulses could have been very damaging to us. In fact, there are some pulsars that are part of a binary system that are called black widow pulsars. Because if the pulses are aligned so that they will hit the companion star, they will cause the companion star to boil off a lot of material. Where does that boiled off material end up? A lot of it ends up with the pulsar. And so the pulsar essentially is eating its companion in that case. Hence the black widow term, or better yet, a cannibal would be good because it's eating its companion. Funny things with pulsars. I talked about some pulsars, they're called microsecond pulsars because it's microseconds between rotations. Pulsars over time are going to lose energy. Why are they losing energy? Because they're emitting energy in those beams that are being created by the magnetic fields. So energy from rotation is being transferred into the energy in the beams that's leaving. So they lose energy, which means they slow down over time. So this graph shows rotational speed slowing over time, but then you have a couple of glitches, a couple uh-ohs, where it speeds up. What could cause it to speed up?
Wait, what caused what to speed up?
What could cause the rotation of a pulsar to speed up?
Can it get closer together like small?
That is one option. It could be because it shrinks a little. That's what it says here. It cools a little. Now these things are really tiny. Because they're really tiny, the amount of radiation that they're losing, the energy they're losing from light, is very small compared to their total energy. So they cool enormously slow. But as they slow, you can have them shrink a little. And so it's spinning along and all of a sudden, it shrinks a little. And for conservation of angular momentum, it spins a little faster. And so that's what's believed these glitches are. Another option is if it has a companion star that's dying. If you have a companion star that's dying, mass of the companion star comes off, and some of it makes it to this star, but as it comes in, it makes it spin faster. So it turns out that a pulsar will slow over time, but the actual fastest spinning pulsars ever discovered are old pulsars with companion stars, because they've been spun up by their companions. So what does a neutron star look like? Approximately 10 kilometers in radius. And the interior, it says, a neutron superfluid. It's really hard to think of something that's as compact as the nucleus of a star, of an atom, being a fluid, but yet that's what they call it. And then in the outer few hundred meters is, you can't read it up there, but a rigid exterior. Very spherical in shape because of gravity. The most massive ever observed neutron star is twice the mass of the sun. Most are between 1 and 3 solar masses. Now somebody might say, wait a minute here. What's the maximum mass you can have for a white dwarf? It's how much? 1.4 solar masses. The previous graph even said that neutron stars have masses over 1.4 solar masses. Because if it's less than 1.4 solar masses, it won't crush the nucleus. So this here mass between 1.1 and 3 solar masses actually contradicts that. I'm not going to go into why some people think that you could be less and some say it can't be less than the Chandrasekhar limit. But just something to keep in mind. Magnetars. Magnetars are pulsars with extremely strong magnetic fields. They probably were extremely large stars. The pulsar that the Earth went through its pulse in 2004 is a magnetar. It's something, did I say how strong its magnetic field was? I think it's 800,000 times the strength of the Earth's magnetic field.
800.
Yeah, 800,000. Very strong magnetic field. And so it's going to cause bursts of very high energy gamma rays. Going back to the deaths of stars again. We've talked about the deaths of stars. The type 1A supernova is the one that produces nothing. A type 1A supernova can only occur in a binary system. Occurs in a binary system where you have two stars, one a lower mass star, one a higher mass star. How does the lifetime compare between a lower mass and a higher mass star? Which one has the longer lifetime? Lower mass has a longer lifetime. So the larger mass star dies first, goes into its giant stage. There's our second picture. The lower mass star is still in the main sequence. And then after its giant stage, if it has a mass less than 1.4 solar masses at death, it becomes a white dwarf. But then its companion starts to go into its red giant stage, and it's blowing off a lot of mass. Some of that mass gets funneled over to the white dwarf. And as it comes into the white dwarf will accumulate more hydrogen gas on its surface. The surface is very hot on these white dwarfs because they shrunk a lot. And so what eventually happens to the mass on the surface of the white dwarf? Reaches high enough temperature and pressure for what happens with hydrogen gas at high enough temperature and pressure? Fusion. So you will have enough temperature and pressure there in the hydrogen gas in the exterior for fusion to occur, and it goes boom! You have a big explosion on the surface. So suddenly a huge amount of light emits. That's called a nova. Nova meaning new. When this occurs, you suddenly have what was very faint in the sky now is very bright. And then life goes on. And this will repeat again and again, reasonably periodic because the rate at which mass accumulates is about the same, until you get to the point where the mass of the white dwarf exceeds the Chandrasekhar limit. What's going to happen when you exceed the Chandrasekhar limit? Then you force electrons into the nuclei, and in this case, it explodes into just a cloud of gas. No core remnant. There's no black hole. There's no neutron star. There is just everything blows up. So that's a type 1A supernova. Everybody understand that type 1A supernova? These last few slides, oh shoot, I should have prepared more because I only have like 3 more slides, are talking about the search for the gamma ray burst that I already talked about. So, actually, I shouldn't have gone so quickly. This here is a map of all of the different gamma ray bursts that they've been able to find. And what they have here in this, you can see that it's what we call isotropic. It's the same in all directions. There's no preference. There's no, oh, we have them here but not there. So they're everywhere, spread out about the same. And here's a picture showing the gamma ray burst that occurred in February of 1997. And here's one from March 2008. Extremely luminous afterglow, it says. Let's talk about black holes. I don't have any slides to go with this. This is all going to be, without slides, without pretty pictures. I have pretty pictures for class on Friday. By the way, before I forget, one person stayed and did the lab quiz last night. So one person, after Thanksgiving break, won't need to come to lab anymore. Now, if that one person has missed lab, they can make up a lab by coming then. I don't know if anyone's missed lab here, but if you missed lab, that's the only way to make up a lab is to do the lab quiz before Thanksgiving break and then come after Thanksgiving break and help people while I'm doing the lab final with others. Okay, black holes. What is the difference fundamentally between a white dwarf and a neutron star?
Like the mass is like 1.4, it has to be no more than that. There you go.
Okay, so white dwarf has to have a mass that's less than 1.4 solar masses. Otherwise, there is enough gravitational force to push electrons into the nucleus. And that causes the white dwarf to suddenly have all of the nuclei converted into neutrons, and we create a neutron star. Now, a neutron star, if you increase the mass enough, you can crush the neutrons as well. And at that point in physics, we don't know of any force that can stop the collapse. And so some scientists believe that all of the mass collapses to a single point, what we call a singularity. So you can take all of the mass in that region and collapse it to a single point. Other scientists believe there's got to be something. There has to be something that keeps it from collapsing to a single point. Something that we don't know about, something we may never know about. But what we do know is that there is a certain escape velocity, a speed that something has to have to get away. So from Earth, if I have something like, if I have a gun and I shoot a bullet, and if there was no atmosphere to interfere with it, if I shoot the bullet fast enough, as long as it doesn't hit the Earth on the way out, it doesn't matter what direction, it'll have enough energy to escape from the Earth. And doing a quick calculation tells us that the speed I would need to shoot a bullet with to escape from the Earth is 11.2 kilometers per second. That's what we call the escape velocity. And the escape velocity depends on the mass of the star and how far you are from the center of the star. So I think it was Thomas More, back before the time of Einstein, predicted that you could conceivably have a star that has such a high density, so much mass and such a small volume, that the escape velocity from the surface of the star is faster than the speed of light. And he hypothesized that the speed to escape is faster than the speed of light, then nothing can escape, including light. And so he called these things dark stars, a theoretical object that has enough mass and small enough volume that not even light can escape. Of course, how would you ever observe such a dark star? What's in here?
Isn't it mid like actions or something they were working
Okay, they do, but the first plain answer is you don't. You don't ever observe a black hole as we call them today. But what you do observe is stuff outside of the black hole. So a black hole is what we call a region where you have mass packed into a small enough volume that not even light can escape. So it doesn't. But stuff that's falling in, as it falls in, it's going to be going faster and faster and faster, getting hotter and hotter, giving off radiation. And so you can see the radiation of stuff falling in. Furthermore, because of magnetic fields, charged particles that are falling in will get redirected and shot out to poles. And so those things shot out, that's the X-rays Mira was talking about. So you can see those. You can see what we call the accretion disk, the stuff orbiting around it, and you can see the jets coming out from it. Did you have a question?
Yeah, I was just wondering, with these black holes, are they generally cold, hot, or can we tell at all just by the outside? That's what I'm saying.
We cannot tell anything about what's going on inside. I mean, we can come up with some theoretical ideas. And you might be aware of like Stephen Hawking proposed what he called Hawking radiation. I don't know if he called it Hawking radiation, if that's what people named it in honor of him because he's the one who came up with the idea. That you could actually have quantum tunneling for matter to come out of a black hole, which is kind of a bizarre thing, which says that if you had a black hole in isolation, it could evaporate over time because you have quantum tunneling, material escaping from it. But basically, we don't know what's inside. We can never know what's inside.
I checked the time.
Oh, yeah, still 10 minutes, but plenty of time. So, going back to the black hole, the temperature outside is going to be exceedingly hot. If you are on a neutron star, the surface gravity on a neutron star is 100 billion times the Earth's surface gravity. So what would happen to you if you somehow magically found yourself on the surface of a neutron star? You'd be crushed. You would also be burned up because the surface temperature is super hot. I think the surface temperature is on the order of hundreds of thousands of kelvins. So you'd be incinerated. If you were even to fall into one of these things, we have the thing called the tidal force. Remember, we have tides on Earth because the gravitational force between the moon and the Earth is stronger on the side closer to the moon and weaker on the side farther from the moon. So there's a difference in the force that has the net result of stretching the Earth. The Earth doesn't flex too much, it does a little. That's a driver of the shifts in platonics in tectonic plates. But the water is much more malleable, so the water elongates, and we can definitely see the tidal forces. Well, if you were falling into a neutron star, or God forbid, a black hole, the tidal forces would be so extreme that you would be stretched so you'd be kilometers long. And it is spaghetti, and millions of kelvins. You know what? Yeah, and dead. All of the sci-fi stuff we see of people going into black holes just can't happen. You would be destroyed in the process. It's really fun to watch Sliders or Contact or Stargate or what is it? Interstellar, or Interstellar. But it's just not realistic. The Interstellar got a lot of acclaim. It had Kip Thorne as its science advisor. You guys probably haven't heard of Kip Thorne, right? He's a very famous astronomer. He's the one who had the bet with Stephen Hawking about whether a black hole really existed. Stephen Hawking took the side of saying black holes don't, we have no observational evidence of a black hole. And Kip Thorne took the side saying we will have observational evidence. And, probably 20 years ago now, Stephen Hawking decided that there was strong enough observational evidence that there was a black hole. Now, Stephen Hawking didn't make this bet thinking there weren't black holes. That would be betting against himself. What he was doing was having some fun, hoping that he would lose the bet. If it turns out that there weren't black holes, at least he would have this winning bet to show for it. The thing that makes me a little sad about the whole story is Stephen Hawking paid off the bet, which was providing a year's subscription to Penthouse Magazine to Kip Thorne. Real high quality bet there. So Kip Thorne was the science advisor for Interstellar. And it got lots of kudos because they had things like a realistic event horizon. The event horizon is the name for the region that's, if you advance beyond it, there's no hope. We call the distance from the center of the black hole to where the escape velocity is the speed of light, the Schwarzschild radius. And so the event horizon for a non-rotating black hole, got to be specific, is a sphere with a radius equal to the Schwarzschild radius. And we often think of black holes as being like disks. After all, when we look at pictures, we see the accretion disk. We think the black hole must be like that. But it's not. The black hole, if it's not spinning, it's going to be spherically symmetric. And so one of the things that everybody was like, woo, about Interstellar was when they're coming up to the black hole, you see a spherical thing. And of course, in reality, what would you see? It would be spherical, but what would you see? Nothing. You'd see a spherical nothingness. But with that much mass, we learned earlier, well, did we really? A mass will warp the space-time continuum. So we talked about gravitational lensing. We can have gravitational lensing from that black hole. So you're going to see stuff coming around, even though you can't see the black hole, you're going to see light that's being bent by it. It's not so much the light being bent as the space-time continuum is misshapen and warped. So when we talk about black holes in class on Friday, we'll talk about this warping of the space-time continuum and how Einstein's understanding of the warping of the space-time continuum redefines what a black hole means. And I am going to stop here because I've got like 15 minutes or, 10 minutes without having any slides. And in a class like this, students just get bored without pretty pictures. Oh, shoot. I forgot to make a homework sign, didn't I? You all were aware of this.
I saw it yesterday. I was like, oh, wait, no home.
I could have sworn on Sunday. I said you had to do it. Well, I guess you won't be turning in a homework assignment today. Let me get busy. You still got a couple hours.
I have 2 papers there.
Yeah.
Well, I'll,
I can't believe I forgot to give you all this assignment.
well, I'll use the time that I was going to work on the homework to go on to
Yeah, I know, we're all
Yeah, that's what Alwan just said.
and practice.